All right, so welcome to the second lesson on equilibrium. Last day we took a look at translational equilibrium, which referred to objects that weren't accelerating in the x or y direction. And today we're going to add to that idea of equilibrium, and except now we're going to look at something called torque. So if a body is in translational equilibrium, that means it's not accelerating side to side and it's not accelerating up or down. However, it could still be rotating. And so think of an example of that. Imagine a teeter-totter with two students sitting on it. And we have a 100 kilogram student sitting on one end and a 50 kilogram student sitting on the other. If you think about all the forces that are acting on this system, we'd have a large force of gravity down on this end and a relatively small force of gravity on that end. Now, of course, that wouldn't be it, because if that was the case, then the seesaw would just fall through the ground. And so the seesaw itself is pushing up with, say, a normal force upwards. Now, if you take a look at this object is not in translational, it is in translational equilibrium, which is to say that the two downwards forces are balanced by this upwards force. And so there are no forces in the x direction. The net translational force in the x direction is 0. But the sum of the forces in the y direction is also 0. However, if you've ever had this experience, you know that this system is not going to just stay like this. What's going to happen is the heavier student is going to kind of rotate downwards, and the lighter student is going to rotate upwards up into the air. And the reason this happens is because of something called torque. So this system has what we call a net torque. And because of that, it is not in equilibrium. Because to be in equilibrium, you have to have both translational and rotational equilibrium. So let's talk a little bit more about what torque is. So this second condition of equilibrium tells us that in order to have no rotation, there must be no net torque. Now, torque is defined as force times distance to a pivot. So the symbol for torque is tau, and this is going to be F times D. So note that torque is the symbol tau. Force, of course, is F, but then this whole point here, distance to the pivot, is D. And so that's different than what we've seen in the past with distance, where you're actually covering ground. Something is moving a certain distance. In this case, what we're talking about is how far removed from the pivot point is the force acting. Now, you'll note that since torque is force times distance, the units of torque are just going to be newtons times meters, or Newton meters. So imagine you're trying to switch the tire in your car, and you're using you need to loosen off all the lug nuts, and you're using a wrench to do so. Obviously, doing it by hand would be very difficult, but if you have a wrench and that wrench is long enough, then it's actually fairly simple. If you need 24 Newton meters of torque to tighten a nut, and you can only apply 100 newtons of force, how long of a wrench do you need? Well, torque is just going to be force times distance, and so the distance that you're going to have to apply that force across will just be torque divided by force, which is 24 Newton meters divided by 100 newtons, which gives us a distance of 0.24 meters, or 24 centimeters. Now, obviously, the way torque works here is that if you needed to apply more torque, but you only had that same amount of force at your disposal, then you could simply use a longer wrench. And you might think of this idea, you may have heard the term leverage. The longer the lever arm that you use, the more leverage you get, or the more torque you can apply. So it's not immediately obvious, but torque is actually a vector quantity. What's a little bit different about torque is that when we talked about vectors in the past, we usually talked about them being positive or negative, left or right, up or down. In this case, torques are either going to be clockwise or counterclockwise. And so when we look at a system, the torques that work in opposition to each other are not rightwards versus leftwards or upwards versus downwards, but instead it's going to be clockwise versus counterclockwise. And so if an object is in rotational equilibrium, what we say is the sum of all torques must be 0. Or, put another way, the clockwise torque has to equal the counterclockwise torque. Now, there's a few terms here that we're going to have to get used to when we talk about systems that are potentially rotating. And the first one here is a little bit strange. It's something called center of gravity. All objects have a center of gravity, and regardless of their shape, there's some point where you can think of some point as being where the average of all the parts that make up the object act. And so for now, we'll think of the center of gravity as being the average position of an object's mass. Which is to say, if you look at all the parts that make something up, if you take the average of all those little parts and you figure out where they are, you'll find the center of gravity. Now, we're going to simplify things often, and we're going to look, when we look at rotating objects, we're often going to assume that they are what we call a uniform beam. A uniform beam is a beam or an object that has constant density and shape. So an example of something that's pretty close to a uniform beam would be, say, a meter stick. You can see that the shape, the thickness, and the width doesn't change much as you go along the length, and the density is going to be the same all across. Okay, last but not least, this is another weird one. We're going to talk about objects rotating. And so an object that's rotating obviously has a pivot, a point that it rotates around. It turns out, though, when we're solving these problems, that that pivot point is arbitrary. And so basically, when solving a problem, you can decide to use any point on that object as your pivot. So basically, one can choose any point as their pivot. And that's going to be a little bit confusing, but we'll see a few examples here where that comes into play. All right, so let's look at the first example. I've got an object here, the kind of problem that only shows up in physics textbooks. I've got a beam that's attached to the wall by a hinge on one end, and then the other end is attached to a rope which goes to the ceiling, and from that beam we're going to hang a sign. Now the beam itself, the pole itself, has negligible mass, so the beam, I don't have to worry about the mass, but the sign has a weight of 350 newtons. And what we're looking for is, we want to know what is the tension in the rope that's holding this all together. So we're going to follow a set of steps whenever we solve these rotation problems. And the first step is to draw all of the forces acting on the system. And we're going to draw these forces as they apply to the beam. And we'll think about this object as potentially rotating and the forces that act on it. So for example, I have a tension pulling up on the beam at this end of, at the far end. There's a weight. This sign has a weight which pulls down. Of course, it pulls on the rope, and the rope pulls on it, which pulls on the beam, etc., etc. And long story short, basically, I have a weight, or an FG, that's pulling down right at this location. So we're going to diagram all of our forces, and the next step is to identify our pivot. So in some cases, it's fairly obvious what we should use as our pivot. Like, for example, this is a hinge attached to a wall, and hinges are pretty good pivots, so let's just choose that as our pivot for now. And then once we've chosen our pivot, the last thing we're going to do before we start messing around with the equations is we're going to just figure out what is the distance of all these forces to the pivot. So for example, FG here is a distance of 1.3 meters. I'm going to call that D1. And the tension here is a distance of 2 meters. I'm going to call that D2. So I'm going to use my second condition of equilibrium, which is torque clockwise must equal torque counterclockwise. And I can see that these two forces are trying to torque the beam in different directions. If I think of this as my pivot point, and I think about it rotating around that pivot, I can see that this force of gravity is trying to torque this in a clockwise direction, whereas the tension is trying to torque in the counterclockwise direction. And so the clockwise torque becomes Fg1 d1, which is equal to tension times d2. And solving for tension, tension is just Fg1 d1 divided by d2. Recall that the weight of the sign was given, so that's 350 newtons, times d1, which we said was 1.3 meters, all divided by 2.0 meters. And then when I crunch the numbers on this, I end up with a force, a tension force of right around 230 newtons. Okay, so I've got my answer, and that's all well and good, but at this point, if you're paying close attention, you should have a problem with this, because something's not quite right. We already said that the force of gravity pulling down here was 350 newtons. And we just calculated that the tension pulling up on this end of the rope was 230 newtons. Well, if those are the only forces in our system, then this can't be right. This beam, this whole system must be accelerating downwards. And so take a look at the next question on the next page. It actually says, what are the vertical and horizontal components of the supporting force provided by the hinge in the last problem? So there's something that we missed, something right back from the beginning when we asked ourselves, hey, what are all the forces on this system? The hinge itself is attached to a wall. And so if you pull or push on that hinge, of course, it can provide some force up or down, left or right. And so when I look at this, I recognize that, wait a second, if I pull down on this with a weight of 350 newtons, and I'm only pulling up on this end of the bar with a tension of 230 newtons, there must be some other force that's pulling upwards here. And I'm going to call that Fy. My supporting force of the hinge, I'm just going to call it a Y force. Now, when you look side to side, these two forces are entirely in the Y direction. There are no other forces in the X direction. So I could say, for example, that the sum of all of the X forces are 0. And so really Fx, the supporting force of the hinge, is 0. The hinge itself doesn't provide any force in the leftwards or rightwards. However, in the Y direction, the sum of all Y forces, which in this case would be the tension force upwards plus the Y supporting force upwards minus the force of gravity downwards, has to add up to 0. Which is just to say that the hinge has to provide the difference between the weight of the sign and the tension. So 350 minus 230 gives me 120 newtons. And so this hinge must be pulling upwards on the beam with 120 newtons of force. Now it's worth considering. Why does the hinge provide less force than the rope? Right? You can see that if the force of the hinge is 120 newtons, the tension is almost double that at 230. Why is there more force of tension than hinge force? All right, let's move ahead and look at another example. So two students sit on opposite ends of a teeter-totter. And the teeter-totter has a weight itself of 800 newtons. Student 1 has a mass of 65 kilograms and sits at the far end. So there's my 65 kilogram student. The other student has a mass of 90 kilograms. How far from the pivot should he sit in order to achieve equilibrium? And so I've got a second student here which isn't sitting at the very end. I know that if this larger student sat at the end, I wouldn't be able to achieve equilibrium. So first step is to draw all of my forces. And so I'll call this student FG1, and their weight is pulling down on that end of the beam. And then over here I've got FG2, their weight pulling down on the beam. But of course those aren't all the forces. Remember that the beam itself has a force of 800 newtons, or a weight of 800 newtons. And so where does that act? Well, if I think of this beam as being a uniform beam, which means it's evenly distributed, its shape, then the weight of that beam would act at its center of gravity, which is the center of the beam itself. So the weight of the beam, I'm going to think of it as acting right at this point. And of course, there must be another force here, otherwise this whole teeter-totter is falling down through the ground, and so there's a relatively large normal force upwards supporting this whole system. Okay, so I've got all my forces diagrammed out. My next step is to identify my pivot point. And again, it's a teeter-totter, so a fairly obvious point to choose might be the very center of the teeter-totter, where it teeters back. Okay, so I've diagrammed my forces and I've chosen my pivot. The next thing is to just label all my distances. So the distance from this first student to the center of the beam, I'll call that D1. And that would be half the length of the beam itself, which is 1.3 meters. And then the distance to the second student to the center of the beam would be D2, and I don't know that yet. So I'm going to start with my first condition of equilibrium, which is to say that torque clockwise has to equal torque counterclockwise. And I can see that this weight, the student here, FG1, if the center of the beam is my pivot, then FG1 is trying to twist this beam, torque this beam in a counterclockwise direction, whereas student 2 is torquing in a clockwise direction. And so I would have FG2 is equal to D2, FG2 times D2 is equal to FG1 times D1. Now, you might notice that there are two other forces here at work, like Fn and Fg3. Why don't they show up in my torque equation? And the reason is simply this, is that those two forces, while they're there and they are acting on this system, they are right at the pivot. I chose this point as being my pivot, and so this force upwards and this force downwards provide no net torque around that pivot because the distance between the forces and the pivot is 0. And if torque is force times distance and the distance is 0, then there is no torque. So you can see this simplifies my, my rotational equilibrium condition because I only need to worry about the forces that are somewhere other than the pivot. Solving this for D2, D2 is going to equal FG1 D1 over FG2. Now recall that FG1 is just M1G and FG2 is just M2G. So substituting those into my equation, I get M1G D1 over M2G. And you might note that the g values cancel out in this case. Substitute in the numbers, I get 65 times 1.3 divided by 90. And so the answer works out to be right around 0.94 meters, which is what I expected, because I knew that this heavier student would have to sit closer to the pivot in order to provide the same amount of torque as a lighter student. All right, we're going to look at one last example here. So in this last example, I've got a truck sitting on a very fancy looking bridge, and the truck is sort of parked part way to the side. Now the truck itself has a mass of 3,500 kilograms, but the bridge deck itself also has a mass of 6,500 kilograms. So first step is to draw all the forces. The weight of the truck would be pushing down on the beam or the bridge deck at this location, so we'll call that FG1. The bridge deck itself has a weight of a mass of 6,500 kilograms. And if we assume that the bridge deck is a uniform beam, then that would be occurring in the center of mass, which is the geometric center here. And so I would have FG2 in this location. Now, of course, presumably the bridge is not falling down, and so the two sides here are supporting it, and that's what we're looking for. What is the supporting force provided by each of the two supports? And so this support would push upwards, and I'll call that FN1. And then this support would also push upwards, and I'll just call that FN2. Now, you'll note that when I drew these forces, I actually drew the arrows as the same size, and that's just because I'm not really sure at this point which force is bigger. I mean, that's something to consider. Is FN1 equal to FN2? Is one of them larger? So maybe keep that in mind. Have an idea of what you think the answer is, and we'll go through and solve and see what we end up with. So the first thing I need to do after my forces I need to choose a pivot. Now, as we said before, we can choose a pivot to be anywhere. In the previous examples, it was really obvious because a teeter-totter or a hinge are obvious pivot points. But what should I choose in this case? I mean, I could choose the center, or I could choose where the truck is, or either end, or anything I want. Just imagine for a second you did choose the center as being your pivot point. When you write your torque equation, you'll have an FN1 on one side and an FN2 on the other side, both of which are unknowns. And so if you have two unknowns, you won't be able to solve your equation. However, if I choose my pivot to be at one end or the other, suppose I choose my pivot to be at this point here, you can see that while I'm going to have FN2 in my torque equation, FN1 is occurring at the pivot point. And if the force is at the pivot point, then it doesn't provide any torque about that pivot because the distance is 0. So I can almost eliminate one of my unknown forces by choosing the pivot to be at that location. And so if I say torque clockwise has to equal torque counterclockwise, and now when I look at all the forces in the system about this pivot, I can see that FG2 and FG1 are both torquing this clockwise, and Fn is torquing counterclockwise. Before I get too far, I should sort out my distances. So for example, from this pivot here, FG1 is a certain distance. I'll call this D1, and that is, I can see that's going to be 15 minus 5 is 10 meters. FG2 is acting at distance D2, which would be half the length of the beam, which would be 7.5 meters. And then I guess the FN2, way at the other end here, would be the full 15 meters. I'll call that D3. So again, torquing clockwise are my two weights. So since there are two forces, both of them torquing in the clockwise directions, I'm just going to sum them up. So FG1 D1 plus FG2 D2 has to equal Fn2 times D3. So Fn2 is going to equal Fg1 D1 plus Fg2 D2 all divided by D3. And remember, of course, that Fg1 is just M1G and Fg2 is just M2G. So substituting those values in, I get M1G D1 plus M2G D2 all divided by D3. And I'm going to put in my values and solve. So 3,500 times 9.8 times a distance of 10 meters from the pivot plus 6,500 times 9.8 times a distance of 7.5 meters from the pivot, all divided by a distance of 15 meters. And this works out to be just over 54,000, 54,717, which I'm just going to round off to say 55,000 newtons. Okay, great. So I've solved for Fn2, which is the right side supporting force. But remember that I need to find both of the supporting forces. So that I need to find Fn1 as well. Now at this point you might say, okay, fine, we chose the pivot on the left side. Let's just move the pivot and redo the calculation. And that would totally work. You could choose the pivot as being the right side, run the numbers, and you'll get the right answer. But that's more work than I want to do. Instead, I'm going to take a little shortcut and just say, well, look, at this point, I know my up force here on the right side. I know both of my down forces. So I'm just going to look at my translational equilibrium equation, which is to say, this bridge is not accelerating up or downwards, or put another way, the sum of the y forces must also be 0. So the two up forces, Fn1 plus Fn2, subtracting the two weights, Fg1 minus Fg2, has to sum up to 0. And so Fn1 is really just the difference between the weights, Fg1 plus Fg2 minus Fn2. And so this is 3,500 times 9.8 plus 6,500 times 9.8 minus 55,000. And this works out to be approximately 43,000 newtons. And so, like we said, from the beginning, we were sort of wondering what's going to happen between Fn1 and Fn2. So interesting to note that Fn2 over on the right side is larger than Fn1. And you might ask yourself why that is. All right, that's it for